So no questions. So a lot of what the lecture that you should have just seen, I believe it is on, just pulling it up, on rotation about bonds, sterics. We're talking about gauche and staggered conformations. And what we're discussing in here, all sorts of problems. We'll do some examples. Yeah, we'll do lots of those. Exactly. That's where I'm going to go. So there's nothing in specific. We're going to walk through some of these. So what we're looking at is what is the difference between torsional strain and steric strain? These are great questions. I love all your questions. So Alyssa, you're getting a bit ahead, but I think I might come into that because some of you guys might be coming into it because it all kind of ties together. We were looking at this bond, and single bonds have free rotation. Like they're just, my camera's not on. Like, I will make this molecule that I just have here. So I have a 4-carbon chain. We draw it kind of as a zigzag. And single bonds have free rotation. You can just spin this guy around as much as you like. Whee! So when you look at it like this, it's hard to tell. It can be sometimes difficult to tell three-dimensionality around a bond. So what we're doing in Newman projection, and let's say in my drawing here on the page, carbon 1, carbon 2, carbon 3, carbon 4, I could ask, draw the most unstable conformation. Newman, in this case, it would, because it's only got 4 carbons, it actually is the most unstable conformation, but I'd probably be more specific. Draw the most unstable conformation as a Newman projection. That's a question. So there's a few things there that you need to figure out. One is, what is the definition of the word conformation? 2 is, what is the definition of the word unstable and what the hell does that have to do with conformation? And 3 is, what is a Newman projection? And I guess 4 is draw. But hopefully we can deal with the drawing. So conformation is shape and bending and when moving bonds. So we can move single bonds all we like. So, you know, all these are different conformations of this molecule. I'm rotating bonds, I'm spinning bonds, doing all that. Those are conformations. If I rotate the molecule, but not change any bonds, those aren't conformations. It's all the same conformation. I'm just changing my viewpoint. That's not different conformations of the same molecule. But if I rotate a bond, that's a different conformation of the same molecule. So it's asking me for a conformation. Conformation is what you get when you can rotate single bonds and molecules can bend. It's asking for the most unstable one. So the most unstable conformation is the one that is, well, it's the one that's least stable. And what that means normally is that you're maximizing sterics. Cool, now we just added another word. So sterics is a fancy word for saying electron clouds bumping into each other. Electrons take up space, they repel each other. And we want to have electrons far away from each other. So this conformation I've drawn here, or I haven't drawn, this conformation I'm holding in my hands, these two methyl groups at the end, these two terminal groups, are pretty close together. Their electron clouds are bumping into each other. That is not favorable. We want the big things away from each other, and the best way we can do that is to point them away from each other. But it's not clear that from just that, like that, what I've drawn, what I'm holding here, with them 180 degrees from each other is considerably better than that. Like here, they're far away from each other too, right? That's pretty good. So why is this better than this? And it's very hard to do, so that's what we're going to use our Newman projections for. So what is a Newman projection? Essentially, it's you have to define the bond you're looking down. So you're going to say that you can't say draw the Newman projection of this molecule. That's a meaningless statement. I can say draw the Newman projection along the bond between carbons 2 and carbons 3 of this molecule, or draw the Newman projection along this bond. So you have to define that, and what you're looking at for a Newman projection is you're looking straight on. So this was carbon 1, carbon 2, carbon 3, carbon 4. So 2 and 3 look straight on 2 and 3. Now, it would have been equally appropriate for you to draw 3 to 2. If I say the bond 2 to 3, whichever one you want in front, that's fine. You can do either. Okay, so let's think about what we're seeing here. So I have this, Molecular Vision's Darling model kit, and it represents bonds as sticks. But bonds aren't like quite sticks, right? They actually have some, like if you draw the sp2 orbital, sp3 orbitals here, you'd have some bulbishness to them, like they'd be kind of balloon animals. And we just have it as a stick. So if you're looking down here, what you really see is you see a circle, and this circle represents the sp2 sigma bond, or sp3, I guess in this case, sigma bond. On the front of your circle, you've got a dot, and that's your front carbon. And if you're doing that, what you're going to see is you're going to have a methyl group, coming into your forehead. You're going to have nothing on here means hydrogen. You're going to have a hydrogen in your, I turn myself around, in your left hand, and a hydrogen in your right hand. Sorry, I have my cameras inverted. So you have a hydrogen in your left hand, hydrogen in your right hand. If you reach out and grab them. So you got this ball. So then you have behind the ball, you've got the other atom. Now you can't see the other atom, it's hidden behind the ball of the orbitals. So it doesn't get a dot or anything. But you see stuff sticking out from around that ball. So what you'll see is I have trouble with left and right, so I need to be very careful with this. In your left hand, you've got a hydrogen, like grabbing it. In your right hand, you've got a hydrogen. And then going straight down, you have another methyl group. So this is a Newman projection. Ball, front carbon with kind of like a propeller shape. Everything's about 109.5 degrees from each other. But when you look at them on an angle like this, they look 120 degrees from each other because perspective's a bitch. Anyways, it's easy to draw. There's no marks off. If I don't get out a protractor and say, oh, it's like 118 degrees, you're wrong. It's about a propeller kind of thingy. Back one's like that too. And what you can do now with the Newman projection is the same thing you can do in reality. So I can rotate that bond. It was up. That was how I had it. So I can rotate the back carbon different angles. Now the worst one I can get is when the back carbon and the front carbon have their big groups lined up right next to each other. That's the worst possible situation. So to get that, what I can do in my drawing is I can rotate either the front or the back carbon 180 degrees. Pick your poison. I'm a back carbon rotator myself, but if you're a front carbon rotator, that is okay. You're still a human being. I'm just going to draw the back carbon in a different color. Notice I'm just trying to draw them more or less where they're going to be. And that's what I see, right? Like looking right down this bond, the hydrogens eclipse each other. Which means, you know, it's like an eclipse of the moon. They're in front of each other. Actually, everything eclipses everything. And my two biggest groups are on top of each other. We're going to come back to what defining biggest group is when we start talking about chairs. But for now, a methyl group is bigger than a hydrogen. That's pretty clear. Hydrogens are small. You actually can't get smaller than hydrogen. So how can you visualize this without a physical model? That's a really good question. Now I'm going to come back to some of these questions. Thank you, Samantha, for answering Amanda's question. Awesome job. Now we got Melitza's and Madison's questions, which I think are both seem separate, but they're actually similar. Melitza asked, do we always look at the middlemost bond? No, I asked to look at the middlemost bond in this case. It's just in this case, the only Newman projection that makes any sense is that one because there's nothing else. We'll go through a more complicated example in a second. And Madison's question, how can you visualize this without a physical model? I'm going to show you. You're going to try. Please get out your physical models, because we're going to start talking about wedges and shapes and things. Okay, let's say we had another molecule. We'll add an extra carbon to be real fancy like. Okay. I'm just changing my mind what to put here. There we go. Okay, let's say we have this molecule. So I've just drawn wedges and dashes for the first time in this course. They were on the assignment. They didn't matter on the assignment. You could ignore them. They meant nothing. But I want to talk about this, what this means. So what they mean is this thick wedge. Imagine, you know, I am going to make the molecule that I've just drawn, and then I'm going to regret having drawn such a complex molecule. Not that bad, but it just requires lots of hopping of bonds. 1, 2, 3, 4. A nice propyl group tagged off the end. And then I need a methyl group. And I need to have a ball. One needs to be careful how one talks about this, because I think I've misplaced all my balls. Around here somewhere. Oh, there's a nice big green ball. Okay. So, what the hell is he pointing at me? Okay, let's point it this way at you. Hopefully, I've drawn. See? Oh, great! I made the enantiomer. Wasn't that clever of me? My camera's inverted, and so I drew the same thing, but my camera's inverted, and so made the enantiomer. So there we go. What do we have here? I'm holding the middle methyl carbon. So we got 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. This final carbon has 2 methyl groups off of it. This carbon number 4 has a methyl group coming out of the page towards me. It is whacking you in the head. And the blue-green ball back here, see this green ball, this represents the fluorine atom and it is going away from you. If you imagine that the page, here's a piece of paper, there is nothing private on it, is the plane of this thing. The methyl group's coming out of the plane. I'm really not good at holding paper. The methyl group's coming out of the plane towards you. The fluorine group is going back into the plane of the paper, and I'm holding it so you can't see it, so maybe I'll hold it here. Like, you can't see the fluorine group because the plane of the paper is in the way. It's going back and away from you. That's what those wedges and dashes mean. So, note wedges get bigger as you get further from the plane. So the thickest, the widest end of the dash coming towards you, the filled in dash, is closest to you. The widest end of the dotted, of the line dash, is the part that's furthest away from you. The Europeans do the line dash backwards and they're wrong, but we're following the North American convention here. It gets very confusing when Europeans and North Americans try to talk to each other about this stuff. You think we would have sorted this one out? Okay. I've also drawn them as triangles. And I want to compare those versus rectangles. So you can draw them as rectangles, like as I just said, closest, furthest, in plane. But you will also see sometimes rectangles. These ones mean absolute stereochemistry. We're going to talk about what I mean by that in a bit. But what I'm saying is that drawing I have there is that molecule. Once I orient it right. The methyl group is coming towards you, the fluorine group is going back and away from you, and that is the way it is. If I had drawn it with these rectangles instead, and you'll see this in the textbook, so instead of wedges, I'd drawn rectangles. That's my best attempt at a rectangle. This is a pair of enantiomers. We're going to talk about what that is, but basically relative stereochemistry. I'm saying that they're opposite each other that way. I'm not with those rectangles, I'm not actually saying it's coming towards you and away from you. I'm saying if this one's coming towards you, that one's going away from you. If this one's going away from you, that one's coming towards you. They're opposite each other. It's two. This means two different molecules. It means both enantiomers. We're going to talk about what enantiomers are later. I just want to introduce this. We'll come back to this rectangle thing. You can kind of forget you saw it unless you want to think about this and you're kind of ahead a little bit in the questions and things. So what the hell does this have to do with Madison's question, which is how can we visualize this without the physical model? Okay, I'm going to start a new page and I'm going to try to remember what I drew. Okay. Let's say my question is draw the most stable Newman projection, most I'd phrase this a little bit more carefully. I'd probably say, draw the most stable conformation as a Newman projection along the 3,4 bonds. Because the Newman projections represent the conformation. Okay, so this is carbon 3 and carbon 4. If you count up priorities and things, you'll minimize your numbers if you start counting at the right instead of the left. And if that's not obvious what I just said, please go back to the ABCs of naming, because this is where I'm going to actually talk a little bit about naming. When we get into stereo, you get another week or so grace before we start talking about naming and enantiomers and diastereomers and other things that end in mers. So how do we do this? How do I do this without a model? Okay, well, if I have a model, it's easy, right? Okay, for a given definition of easy, I figure out where my biggest things are. My biggest thing is this giant freaking ethyl group. My biggest thing on this carbon is this isopropyl group. I want them opposite to each other. Good. I point them in a Newman projection directly at my camera, I hope. And I draw the Newman projection. That's good. Model kits, your friend. Get your model kits out when you're doing this. If you have any trouble with what I'm going to show you next, please, please, please get your model kit out. Okay. Now, if I don't have a model kit, or I have a model kit and I have a timed exam, and so if I made every freaking molecule with a model kit, I would never finish my timed exam. What I can do is I can pretend that I am an eye in the plane of the page. So imagine that you are an eye right where I drew you. Close your eyes and, well, okay, draw a circle, then close your eyes, or don't close your eyes. Open your inner eye. This class finishes a little bit better than Game of Thrones, but that's not saying much. Most torture sessions and better than Game of Thrones. So if we're looking down there, what we're going to see is directly below us, I have an isopropyl group. Now, your priority with this, and it says the most stable conformation, like, well, what if the Newman projection I'm drawing isn't the most stable conformation? Draw the freaking Newman projection first, then rotate it. Don't try and do multiple things at once. Have a stick drawing, draw the Newman projection, rotate the Newman projection, or have a stick drawing, rotate the stick drawing, draw that, draw the Newman projection. Don't try and do this in your head. Not saying you can't. I've been doing this a long time. I can do it. You guys haven't been doing this a long time, because for some people this might be the first time you're seeing Newman projections. So draw all the steps in between until you're really, really comfortable. Okay, in my eye right below me, I'm seeing an isopropyl group. Now, I am in the plane of the page. The methyl group is coming out of the plane of the page. Here is the plane of the page. Right, my eye is right down there. I'm reaching out with my left hand. And I'm grabbing the methyl group. Because if my eye is down there, there is a methyl group up there. You want to see it with the page. I've convinced you that's what I'm looking at. This is where now I'm in trouble because I've drawn the enantiomer to what I have on a page. Sorry, I've drawn the enantiomer to what I have on a page, so I think this works out with my inverted camera. Let me just see. Nope, my camera is maybe not as inverted as I thought it was. I'm getting very confused by my camera. Oh shit, yes it is, because I'm looking down this, but you guys are looking the wrong way. Bugger. Because I have to invert my view because it's you guys who are looking at this. There. So that's the view. You're looking from the carbon with the methyl group. And so if you reach out with your left hand towards that, it's closer to you, you're going to grab the methyl group. So I'm pretending I am in the page, and I'm reaching out with my left hand, and there's a methyl group there. And then when I rotate on the left-hand side, there is a methyl group. On the right-hand side, there's a hydrogen. Then I got my back carbon behind me. And what I see sticking out from the top of this ball, and if you want to draw the ball and draw the ball like a sausage, a hot dog, is I see an ethyl group. Now, in my mind's eye, the fluorine is going back into the plane. And so when my eye is there in the plane, it is in my right hand. I am grabbing that methyl group with my right hand. So when I rotate, fluorine is here in my right hand. The hydrogen is in my left hand. They wanted the most stable conformation, so the next thing I need to do, so I'm blaming somebody else. Like I'm going to say they, it was me, but I'm going to pretend it's a they. Those are my two biggest groups. I could have identified that before I did it. Fortunately, they're opposite each other. Nothing is eclipsed. Everything is staggered. Otherwise known as not eclipsed. So we got about 60 degrees between absolutely everything on there. The only other term we're going to be running into, and that you'll run into in there, and I talk about it in the lectures, but just in case, is that we refer to these two groups as gauche to each other. Which means, you know, left in French, but in English it means awkward. And they're awkward to each other because they're 60 degrees away, and that's still a little too close for comfort. They prefer to be further. But everything prefers to be eclipsed than staggered, and then things prefer to be anti than gauche. And those are your options. Okay, great. So the question was from Faith, is it Christian? Why can't you see the carbon circled in blue? Aren't they parallel to the axis we're looking from, just like the 3-4 bond? It's because I kind of lied. This has to be either out or back. It can be either, and we're going to talk about why it can be either, and it doesn't matter. But they're not actually both in the plane. We draw them both in the plane because it doesn't matter, and it's convention. And I shouldn't have done that. So I am just going to actually assign it arbitrarily that way, and I can then draw it that way down here too. But I've just made this more complicated because now there's more stereochemistry. So how about we don't? And we're going to talk about why we can do that. So at this point, because there's no real interesting information here, I'm not trying to draw that in 3 dimensions. If I was, you'd be absolutely right. We'd have to kind of orient it and change it and rotate it and worry about that. But I'm only really worried about the 3-dimensionality of this bond right around the Newman projection. No, this is just straight lines. It's just I'm very incompetent at drawing. I think I was trying to emphasize something for some reason. Is it wrong to draw the ethyl group bent towards the methyl group? No, it's not wrong to draw the ethyl group bent towards the methyl group. With the Newman projection, the only thing we're interested is in the relative orientation of these six. Nothing else matters. Just the 6 points sticking out of the ball is all we care about with the Newman projection. Everything else is fine. This makes me feel better, Faith, but it doesn't matter. It's right. Both ways are right. Let's try another one. Okay, so same question, draw the most stable conformation as the Newman projection of the indicated bond. I haven't indicated a bond yet, so I'm about to. There. So I prefer asking a question like this because I can ask you to do the numbering, but somebody's inevitably going to number it wrong, and then I'm evaluating not what I want to evaluate. So depending how hungry I am when I'm writing the exam, because I get hangry, that really determines how I ask this question. I will accept snacks for exam writing to keep me out from not being hangry when I'm doing it. I'm kidding. So we can do two things here. We can either find what the most stable conformation is going to be, or we can just draw the Newman projection first. Let's do with just drawing a Newman projection first, because then we're going to practice rotating the Newman projections. Okay, this time, just for shits and giggles, I am going to look from this side. So what I want to do is I want to line my, I still do this. I physically draw in my eyeballs on these things. I like it because then I don't forget where my eye is and which one I'm doing. Again, because I switch back and forth between looking at it from different sides. I'm going to draw in our hot dog. There's our hot, whatever. It looks like many things. I'll put it that way. So if I'm looking up that way, right above my head is a methyl group. It's on the front carbon. This methyl group right here. Now imagine you're in there and you reach out with your right hand and you grab an isopropyl group, right? This group here is in my right hand if I'm standing down here. Right hand isopropyl group. There's nothing indicated in the left side, so that must be a hydrogen. Note that I don't need to, I'm just using the vertex thing. This means there's a carbon at the end of every one of these vertices, right? Okay. On the top carbon, the one away from me, straight down there is an isobutyl group. I've got soup on my screen. In my right hand, above my head, but in my right hand, from that view, is the fluorine atom. And in my left hand is a hydrogen, because there's nothing there. You can do a few things to check to see if you've done this right. I note from here that both the isopropyl group and the fluorine group are sticking out toward, like in the same direction. They're both out. So in my Newman projection, they better both be on the same side of the Newman projection, and they are. The isopropyl group is to the right, fluorine is also to the right. That makes sense because they're on the same side. Now, we've converted a line drawing into a Newman projection. Now we need to rotate the Newman projection to the most stable conformation. But to do that, we need to know what the most stable conformation is. And to do that, we need to identify which are the sterically biggest groups. So Steric. Somebody used the right term up there because they talk about steric and torsional. Strain. There we go. Steric strain. I just couldn't think of the word strain. Steric strain. Electron clouds bumping into each other unnecessarily. It's all relative. It's all relative to the lowest possible for the molecule. You need 50%, Mohammed, to pass the class. But yes. If there's nothing drawn, there's always a hydrogen. So every carbon, if we were going back to that line drawing class, I think that Dr. Hayward did on class number 2, every tetrahedral carbon, like methane, it's a good point, I don't think I've explicitly said this. We've drawn methane like this using Lewis structure. What that actually means is this. You can always draw 2 of the bonds in the plane, one coming out, one going back. Every tetrahedral carbon can be drawn, every tetrahedral atom can be drawn that way. And basically that is a function of, you know, how tetrahedrons work, right? This is a tetrahedron in the middle. I can draw, if I have 2 of them in the plane, one is coming out towards me, one is going back and away from me. I can choose another 2 to be in the plane. One is coming towards me, one is going back and away from me. Any two I choose to be in a plane, I always have one coming towards me, one going back and away from me. And note that the plane kind of forms a V, and the out and back are on sort of the back side of the V. And that's what we have drawn here. The methyl group that's pointing upward, would that be coming towards you as well from that point of view, like a tetrahedron? This one is what you're talking about, Caroline? Caroline? Yeah. What we're looking at there is we're looking straight on, so it's kind of like a propeller. All 3 of them are coming towards you by the same amount, and the other one is going back and away. Like the carbon that's hidden by that ball is like straight back and away, but all these are kind of, these 3 are all in a plane, but the bonds aren't in a plane. But they're all kind of coming towards you. So this one is as close to your forehead as that one is that one. They're all kind of sticking in your face. I don't know if that helps. But yeah, it's coming towards you. Yeah. Model kit. Like, I'm encourage you class 1 to buy a model kit, and you've had a few weeks. This is why you need a model kit. It really, really helps. Once you get used to it, you won't need the model kit anymore. But initially you do. I think the only people in this class who right now are feeling 100% comfortable about everything that's going on here are anyone who happens to also be an architect student. There aren't a lot of chemistry architecture crossover students. Anyone who's got a lot of experience in sculpture. I think you're used to probably thinking in 3D and you're like, this isn't that hard to manipulate and rotate this in my brain. Maybe some of you who do some graphic design. But most of us, and I include myself in this, really struggle at doing 3-dimensional representations of things. I've gotten very good at it, but that's because this is all I do. It's hard. It really is. If you're struggling with this, you can go back through all these structures with the model kit. I'm trying to show it to you through a camera. That sucks. I will, to be honest, say it is slightly better than standing in front of a class with a giant inflatable model kit. That's a lot more fun because the balls are really big. But it's actually not really that visible. It's not that useful. The camera is actually better, but there is nothing like getting out your model kit and going through these again. And I would do all the practice questions with the model kit until you like, I see it. Like you literally see the three-dimensionality in the 2D structure. I can no longer unsee it. But I know it isn't there for, I would say most of you are probably really struggling with this. And that's normal. You've never done this before. It's hard. Please get out a model kit. I would normally say that at the end of the class, I have students coming back to me like the last week of class, and they say, hey, I'm really struggling with all this three-dimensional stuff. And I say, well, okay, how will you get out your model kit? And we'll talk about this. And like, well, I don't have a model kit. And at that point, it's, I'm sorry that this costs extra money. I really am. It's unfair. I get that. But it's kind of, you can avoid that if you're finding some way to compensate and like you're coming to me with like toothpicks and marshmallows. But it's, if you can't get this and you're not using an aid to do it, there's sort of a horse and water thing here. I can't make you drink. So get the model kit. It's going to make your life a lot easier. It's not too late. Okay, so what we need to do is we need to rotate this thing to get the most stable conformation. But to do that, we need to identify what is the most stable conformation. And that's when the two biggest things are furthest away from each other. And everything is staggered. Nothing wants to be gauche. Gauche is bad. Sorry, gauche is okay. Nothing wants to be eclipsed. I meant eclipsed. Everything is staggered. Nothing is eclipsed. The wedges are not drawn in Newman projections, because we're drawing three-dimensionality through the Newman projection. We don't need to draw the wedges. If there were some other wedges somewhere else on the molecule, Lauren, like there was something else attached to it, we'd keep those intact. I'll do another example like that later, just to clarify exactly what I'm meaning as a final example. Let's just take this. So we take this, and I'm going to do a rotation. And I'm going to draw my arrow because I'm going to identify that the two biggest groups here are this terbutyl group and this isopropyl group. Like on the back carbon, that's all I'm comparing is carbon to carbon. So on this back carbon, it's got a hydrogen, a fluorine, and a terbutyl group. Hydrogen is the smallest thing possible. Fluorine is actually the second smallest thing possible because it's, you know, got its full octet. All the electrons are pulled in real tight into the nucleus because there's extra protons in there. So the shell is as smallest as possible on the far right hand side. And a huge ass terbutyl group. And on the front carbon, we've got a methyl group, which isn't tiny, a hydrogen group, which is the smallest thing possible, and an isopropyl group that is a methyl group with two carbons attached instead of hydrogen, so it's obviously bigger than hydrogen. So the things I have in green are the two biggest things. So to get those away from each other as much as possible, I need to do a 120-degree rotation, and I'm going to rotate the front one. So start by drawing a circle. I can draw a circle. Actually, I can't draw circles. That's clearly not a circle. I am just going to draw in the back one because I'm not rotating it. So blah, 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 nothing changes. Back carbon, nothing changes. Front carbon, I've rotated 120 degrees. So this is really important. You don't get confused. I realize the irony of saying that. This isopropyl group is now pointing straight up. I have rotated 120 degrees. It was there. It is now there. Everything is going to move counterclockwise. The methyl group that was straight up is rotated 120 degrees. Again, counterclockwise. So it is now down here on the left. It has to be. And the hydrogen has rotated counterclockwise 120 degrees and is there. Okay, now the other way this can go is, what if we need to go from a Newman projection to a line drawing? So let's say we had a Newman projection. Some whacked out molecule. Why not? Just random atoms everywhere. And I say, okay, now turn that into, I'm actually gonna make one change to this. So turn that into a standard line angle drawing formula. Okay. So with the standard line drawing angle formula, what we want is we want the carbon atoms all in the plane of the page. That's not going to happen if I unfold this because those carbons are not in the plane, because the plane is there. So what I need to do is I need to convert my Newman projection. I can do this either way. I can either turn to the line angle and rotate there, or I can rotate the Newman. I think it's easier to rotate the Newman. So I'm going to rotate the back carbon 60 degrees, and I'm going to rotate the front carbon 60 degrees. And when I do both of those rotations, ball, I draw the front carbon. Methyl group is now straight down. The iodine has moved up to this spot in the propeller, and the fluorine has moved up to that spot in the propeller. The back carbon, the methyl group is now straight up. This OH group, which was kind of up to the left, is now down to the left. Again, it needs to be 120 degrees from there. It's got nowhere else it can go. And the ammonia group, amine, is now down to the right. Now I've got my carbon chain all lined up neatly 180 degrees from each other. So it's in the proper conformation to turn it into a line angle formula. Now I just do the opposite. So my front carbon has a carbon pointing down. And it's got the ball. And then the back carbon has a carbon pointing up. And all of that is in the same plane. It's in the plane of the page. On my front carbon, in my left hand, I'm holding an iodine. So if I put myself in the plane of the page and I rotate myself, it's back into the page. It's behind the page because my plane is here. For me, it's back, I think, because again, camera. But if you try and do this and you don't have your camera on, hopefully you agree. And in my right hand, I'm holding a fluorine, which will probably explode. Then on the back carbon, I have an OH in my left hand. And I have an NH2 in my right hand. Now I'm going to delete my circle because that's not part of the formula. And you can keep the I there. I'm not going to hold it against you. I have drawn the line angle drawing in its most standard conformation, not necessarily most stable, most standard, which is all the carbons in a chain. And I'm done. So you can go from a Newman to a line angle, or you can go from a line angle to a Newman. Any questions about this or anything? Any other examples? Yes. When you draw a line angle drawing, the carbons are almost all the main carbon chain is almost always drawn in the plane. So let's ask, so do you need to always put the carbons in a line? Yeah, in a line angle formula, you should. Okay. If there are no other questions, I'm going to bring this to a close. I'm going to end on time for once, and I will put I'll put up today's. Oh, Madison gets in with another one. How do you know how many carbons are present in a carbon chain? Drake wants to go to the last slide. How do I know how many carbons are present in a carbon chain when comparing Newman? My mouth don't work good. A Newman projection is always 2 carbons in the circle. There's one in the front, one in the back. So there's always 2 carbons there. Everything else is the same. So here there's 4 carbons. There's 1 carbon in the back, that's 2. 1 carbon in the front, that's 3. 1 carbon over here, that's 4. So 1, 2, 3, 4. There's always 2 carbons in a Newman. I don't think I have ever drawn a Newman projection between atoms that are not carbons, because carbons are tetrahedrals. This one really is relevant for carbon. Okay, I think we're good. I am going to stop recording now.